Recently, the Webb Telescope has questioned our cosmological model with its incredible new discoveries. All these discoveries of the Webb Telescope are asking us the same question. Did our universe come into existence 14 billion years ago? Because Webb Telescope has discovered such galaxies which are older than our universe. Astronomers have said that an event in the future will be able to solve this puzzle, which will confirm that when our universe really came into existence. Ever since humans began to understand the universe, they have been asking the question, when did the universe come into existence? And to solve this question, many scientists have given their ideas, which will help to know the age of the universe. If you would calculate the age of all the people who ever lived on Earth, it wouldn't even come close to the age of the universe. So how old is the universe? In general, many consider that the age of our universe is 13.8 billion years. We have made the evolution model of the universe on this timeline, and we named it the Big Bang Theory. So are our calculations about the age of the universe correct? Well, no. One of the most debated topics in astronomy is how old the universe is, and every time we seem to get closer to an estimated number, some new discovery comes out and blows that away. Like new discoveries from the Webb Telescope are challenging our model. Well, these discoveries didn't prove our model wrong. Rather, they are telling us to improve our current model. More about this, check here. The Hubble constant is one of the most important numbers in cosmology, because it tells us how fast the universe is expanding, which can be used to determine the age of the universe and its history.
Thanks to astronomer Edwin Hubble and others, scientists have known since 1929 that our universe is expanding. Its current rate of expansion is called Hubble's constant, or H0. There are two leading ways to measure H0, and for 15 years, they more or less agreed with one another. Not anymore, and that's a big deal. Here's why. In the standard model of cosmology, H0 is a crucial ingredient, right up there with the speed of light. H0 factors into everything we know about the universe: how old it is, how big it is, what it's made of. If H0 is tweaked, we get a different age of the universe, different relative amounts of matter, dark energy, and so on. Unlike the speed of light, however, scientists can't measure H0 in the laboratory. Instead, H0 has to be inferred from observations of the universe. One way scientists have measured H0 is to use observations of type 1a supernovae combined with their host galaxies' redshifts. Each 1a supernova releases roughly the same amount of light when it explodes. Measuring the amount of light we receive from a 1a supernova tells us its distance. Measuring an object's redshift, or its increase in wavelength, tells us how fast that object is moving away from Earth. Researchers use many 1a supernovae as distance markers, measuring objects in our local universe, then moving out to get a measurement of the universe's rate of expansion. The other H0 measurement technique looks at the cosmic microwave background, or CMB, the afterglow from the Big Bang itself. The early universe was hot and dense. Light couldn't travel freely through space. As the universe cooled, the photons were released. This radiation left an imprint, providing insights into the composition of the universe at that time. The CMB can be used to make measurements from the early universe, such as the density of dark matter and dark energy. Those measurements can be combined with the model of the evolution of the universe, allowing researchers to infer the rate of expansion of the universe, or Hubble's constant. As these two camps have improved their abilities to measure H0, it has become clear that they disagree. A recent study using the first method yielded an 8% greater expansion rate than the second method's result. Now scientists are asking, are we missing something? Wendy Friedman, Sullivan Professor of Astronomy and Astrophysics at the University of Chicago, says, it could be that we don't understand the uncertainties well enough to know why these two methods differ. Friedman led a 2001 study using the Hubble Space Telescope to measure H0 via the first method, and is leading a new project to measure it more accurately. Another intriguing question: is it incorrect to expect agreement in these measurements of H0? Maybe the standard model of cosmology, which predicts agreement, is wrong. That would send researchers on an exciting search for a new model of the cosmos. Do we really know what makes up all of the radiation in the Big Bang, wonders Friedman? Is there a new kind of particle we aren't accounting for? Or are dark energies or dark matter's properties changing over time? Over the next few years, researchers like Friedman will be trying to poke holes in how each method conducts its analysis before possibly invoking a revised model of cosmology.
Despite nearly 100 years of astronomical measurements and calculations, scientists still can't agree on the exact value of the Hubble constant. The true number could reveal missing pieces in our understanding of physics, like new particles or a new form of dark energy. But recently scientists have said that we may have found a way to settle this debate. A meandering trek taken by light from a remote supernova, in the constellation Cetus, may help researchers to end this debate in another couple of decades. About 10 billion years ago, a star exploded in a far-off galaxy, named MRGM 0138. Light from that explosion later encountered a cluster of galaxies, whose gravity bent the light. In 2016, an observation from the Hubble Telescope found 3 bright points in a galaxy cluster. Astronomer Steve Rodney says the original 3 points of light that appeared in this Hubble image was purely an accident. 3 years later, when Hubble reobserved the galaxy cluster, it saw all the points of light vanished. With these observations, astronomers concluded that it was a supernova, and they named it SN Requiem. But astronomer Rodney and his colleagues predict that the supernova will reappear in 2037. Because some of the light from the supernova is traveling a long way due to gravitational lensing. If this supernova does indeed reappear in the year 2037, as predicted by astronomers, then a 21-year time delay, from 2016 to 2037, will be a record for a supernova. This time delay could provide a perfect estimate for the distance to the supernova's host galaxy. And this calculation can give us the exact value of the Hubble constant. The longer it takes for supernova Requiem to reappear, the farther from Earth the host galaxy is, which means a lower Hubble constant and an older universe. So, if the debate over the Hubble constant persists into the 2030s, the exact date the supernova springs back to life could help resolve the dispute and nail down a fundamental cosmological parameter. Right now, the Hubble constant ranges from 67 to 73 kilometers per second per megaparsec. But that spread still makes the age of the universe uncertain. The often cited age of 13.8 billion years corresponds to the Hubble constant of 67.4. If this supernova observation yields a different value of the Hubble constant, then the universe could be more or less than 13.8 billion years old. And we have to rethink our current cosmological model and its evolution.